In this three-part video series, we're going to review the process of drawing Lewis structures of both ionic and covalent compounds, as well as expand upon your knowledge from Science 10 by showing how electronegativity can be used in order to determine what type of bonding exists within the compound. Now, the first thing that you should remember about Lewis structures is that they appear superficially simpler than that of a Bohr diagram, because the primary purpose of a Lewis structure is to show how multiple elements are bonded to one another, as opposed to the structures of each individual atom within the compound. And consequently, Lewis structures only really contain three pieces of information. Firstly, and most obviously, are the chemical symbols of the elements, because we need to know what elements actually make up the compound. And secondly, we have the bonds, which tells us how the individual atoms are bonded or connected with one another. In a covalent compound, these would be the locations at which electrons are shared, and in ionic compounds, such as the one that we see here, it would be the charges to show how the ionic positive-negative attraction is formed. Now, regardless of whether we're looking at an ionic or a covalent compound, this type of bonding only takes place between the valence electrons, meaning that all of the electrons that are inside of an element's outer shell are not relevant to the process of drawing a Lewis structure. Now, with Lewis structures and structural chemistry in general, the easiest way to understand it is just to actually jump in and look at the structures of a couple of compounds, firstly ionic compounds, by simply constructing them. Now, in this case, what we will want to do first, regardless of what type of Lewis structure we're drawing, is to draw the Lewis structures of the atoms that make up the compound first before they bond to each other. And in doing so, what we're going to do is to count the total number of valence electrons so that we know what our final structure is going to look like. So we can do it with both of these compounds here. So if we check our periodic table for aluminum, fluorine, potassium, and oxygen, what we are looking for is two pieces of information for each element. The first is the number of valence electrons that each element has. So remember from the periodic table that your alkali metals will have one valence electron, alkaline earth metals will have two, the group that contains boron, aluminum, etc. is going to have three, the group that contains carbon and silicon will have four, and so on down the period until we get to the noble gases that don't form bonds at all because they have 8 valence electrons. Now, the purpose of this video is to connect our knowledge of electronegativity and bonding. So what we want to show by comparing electronegativity values is that these compounds in this video will specifically form ionic compounds. So let's make a mental note. Aluminum's electronegativity is 1.6, oxygen's is 3.4, fluorine's is 4.0, and potassium's is 0.8. So remember those. And I'm just going to write all of those electronegativities above each of the elements here. And after we have these, we can write the total number of valence electrons that each element has. And this is going to be our starting point for constructing Lewis structures. So the first thing that we're going to do before we calculate the electronegativity difference and average electronegativity is actually to count the total number of electrons that we're dealing with. So fluorine has 7, and there are 3 fluorine atoms in aluminum fluoride, so 7 times 3 means that fluorine is bringing a total of 21 electrons, plus the 3 electrons from aluminum means that our electron total is 24 in this case. For potassium oxide, potassium has 1 valence electron times 2 for 2 potassium ions is, 2, and then oxygen brings with it 6 valence electrons, which means that we're dealing with a much similar or simpler total of 8. Now comes the time for us to justify whether we need to draw an ionic Lewis structure or a covalent one by doing our electronegativity difference and our electronegativity average calculations. So if we start with aluminum fluoride, 4.0 minus 1.6 brings us to a total of 2.4, which is a pretty large difference. And then if we calculate the mean electronegativity, we have a total of 5.6. 5.6 divided by 2 brings us to a total of 2.8. So this is our average, and this is our difference. If we repeat these calculations for potassium and oxygen, 3.4 minus 0.8 is going to be quite a large number no matter what. So this comes to 2.6, which we see is pretty close to the electronegativity difference in aluminum fluoride. And then if we do our average electronegativity calculation, 3.4 plus 0.8 comes to 4.2. So our average electronegativity, if we divide this number by 2, comes to 2.1. So then we can go and do the comparison of delta En versus average En. So if we do this for aluminum fluoride, difference is 2.4, average is 2.8, 2.4 is here, and 2.8 is here. So this technically falls almost outside, but we can see that this clearly falls within the ionic range. And then if we repeat this for potassium oxide, difference is 2.6, average electronegativity is 2.1. So if we find average electronegativity here, and a difference of 2.6 is all the way about here, so we can see that both of these fall clearly within the ionic range, which means that we can go ahead and start our Lewis structure building. So now that we have confirmed that both of these form ionic Lewis structures, the next thing we need to do is to find the central atom in each of these structures, which is always going to be the atom that contains the most unpaired valence electrons. And now an unpaired valence electron is something like this, or this, or this, because these valence electrons are available in order to either be lost or gained, and do not form this type of pair, which are what we call lone pairs of electrons, meaning that they are not shared or transferred between elements. So in aluminum fluoride, we can clearly see that aluminum has the greatest number of unpaired electrons, so we're going to put it right in the center with the 3 fluorine atoms surrounding it like this. Likewise, we can see that oxygen has 2 unpaired, whereas potassium only has 1, so we can put oxygen in the center with the 2 potassium atoms around like this. Next, we need to, because we are building ionic compounds, we need to turn each atom into the proper ion, meaning that we are going to give each atom a full valence shell of electrons. Now, in the case of metals like aluminum and potassium, this means that they are going to lose electrons, which means all that we need to do is put brackets around them like this to indicate that they have charge. Now, because with aluminum, losing 3 is easier than gaining 5, when it loses its 3 valence electrons, it is going to have a positive 3 charge, which we can write outside of the brackets like this. And likewise with potassium, when it loses its 1, which is easier than gaining 7, it is going to have a positive 1 charge like this. However, if we are dealing with nonmetals here, nonmetals gain their full valence shell by gaining electrons. So in the case of oxygen, oxygen is going to take the 1 valence electron from each potassium ion in order to get its full octet, which would look like this. And then we can add brackets around it like this and add the charge number here in order to indicate that oxygen has gained 2 electrons. And with aluminum fluoride, because fluorine gains 1 electron more easily than it loses 7, we can give each of the fluorine ions here a full valence shell and a -1 charge to indicate that it has gained 1 electron, and then we simply repeat the process with each of the fluorines, 1, 2, 3, 4, 5, 6, 7, 8, add brackets to indicate that it is an ion, and add the -1 charge to indicate that it has gained 1 electron. Now you'll see that I've kind of combined steps 3 and 4, where we add the brackets around the ion and the charge to indicate the number of electrons lost or gained, but once this is done, we can begin our final check. So remember how we counted the total number of valence electrons that are available to us. This number should match the total number of valence electrons that we see. So aluminum has lost all of its, so we don't see any here, but if we count the valence electrons in fluorines, 2, 4, 6, 8, 8 plus 8 is 16, plus 8 is 24, so it matches, and we are good. Likewise, with potassium oxide, we started with 8 valence electrons, and oxygen has 2, 4, 6, 8, which matches, so we are good. And that is our summary of how to draw ionic Lewis structures. Before you watch the video outlining how to draw covalent Lewis structures, see if you can draw the following ionic compounds below, as well as use electronegativity difference and average in order to determine that an ionic Lewis structure is what we need to draw in the first place.